Welcome everyone. Today, we will be discussing the paper, Central Control over Distributed Routing. This paper proposes a new approach to routing in computer networks, where a centralized controller has more control over the routing decisions made by individual routers. Let's dive in. Software-defined networking is based on an antithetical architecture with respect to traditional networking. In traditional networking, routing decisions are made by distributed protocols such as interior gateway protocols and multi-protocol label switching. However, in SDN, routing decisions are centralized and managed by a software controller using protocols such as OpenFlow and segment routing. Let's explore the differences between these two approaches in more detail. Centralization improves network manageability, flexibility, and scalability, but sacrifices the robustness of distributed protocols such as interior gateway protocols and tunneling protocols like resource reservation protocol traffic engineering. SDN architectures are designed to provide high manageability, flexibility, and scalability, but their robustness is by design lower than traditional distributed networking approaches. To combine the best of both worlds from SDN and distributed networking, the paper introduces FIBBING, which is a hybrid approach that aims to provide both centralized control and distributed routing robustness. Let's dive in to learn more. Due to the design of FIBBING, it offers high standards of manageability, flexibility, scalability, and robustness, offering the best of both SDN and distributed routing. With FIBBING, a centralized controller can make routing decisions while still relying on distributed protocols for redundancy and failover. This balance makes FIBBING a promising approach for network management. FIBBING offers high manageability, flexibility, scalability, and robustness, unlike traditional SDN which sacrifices robustness for centralization. With FIBBING, a centralized controller has per destination full control, but some functions are still distributed thanks to partial distribution. This hybrid approach combines the best of both worlds, offering centralized control where needed and distributed protocols for redundancy and failover. Now let's dive deeper into benefits of FIBBING. We'll start by exploring manageability, followed by flexibility, scalability, and robustness. In traditional SDN, high manageability is achieved by centralizing both computation and installation requirements. For example, an OpenFlow controller or an RCP computes paths, derives FIB entries, and installs them into network elements. FIBBING leverages this centralized approach to manage network traffic, providing per destination full control to a centralized controller. Let's explore how FIBBING achieves this in more detail. FIBBING achieves the same level of manageability as SDN, but centralizes only high-level decisions. The FIBBING controller computes paths, deriving FIB entries, and distributes them to network elements. FIBBING's hybrid approach allows for partial distribution, which ensures that the network remains resilient in the face of failures. Let's take a closer look at how FIBBING centralizes high-level decisions. FIBBING keeps installation distributed, relying on distributed protocols to distribute FIB entries to the network elements. The FIBBING controller only provides high-level instructions, such as which FIB entries to distribute, but relies on the network elements themselves to install these entries. This partial distribution allows for the network to remain robust in the face of failures and ensures that FIBBING remains scalable even in large-scale networks. Let's explore how FIBBING leverages distributed installation in more detail. Distributed installation in FIBBING is controlled by injecting carefully computed information into control plane messages. These messages are sent to the network elements, which then install the FIB entries based on the information received. Let's dive deeper into how FIBBING controls distributed installation. To control distributed installation in FIBBING, it injects carefully computed information into control plane messages. For link state IGP routing protocols, this information includes a weighted topology, which is used by the shortest path computation function to compute forwarding paths. Forwarding paths are provided either by network operators or by controller optimizers such as DEFO. These paths are computed based on the network topology and the desired routing policies. To control the output of an intra-domain routing protocol such as a link state IGP, the FIBBING controller inverts the shortest path function. This is done by injecting carefully computed information into the control plane messages, which guides the selection of paths through the network. In more detail, the fibbing controller computes the shortest path tree for each destination in the network, and then selects the set of links that should not be used for each tree. These links are marked as unavailable in the control plane messages, which effectively modifies the shortest path computation by avoiding the use of certain links. By carefully selecting the set of unavailable links, the fibbing controller is able to control the output of the IGP and enforce a wide range of routing policies. For example, the controller can ensure that traffic is evenly distributed across the network, or that certain links are never used due to their high cost or low reliability. Inverting the shortest path function is just one of the many techniques used by fibbing to control the output of distributed routing protocols. Next, we dive into the details of achieving flexibility with fibbing. Let's consider a simple network topology where we want to send traffic from source C to destination D, while the shortest path is obviously the direct path from C to D. D is also reachable through the path of CABD, albeit with a higher cost. In traditional distributed networking using IGP, an IGP control plane computes the shortest paths on a shared weighted topology. Each node then populates its forwarding table based on these shortest paths. In IGP-based distributed networking, the shortest paths computed by the control plane are translated into forwarding paths on the data plane. This means that traffic is forwarded based on the shortest path computed by the control plane, without any additional intelligence or flexibility in the data plane. However, in fibbing, operators have more control over the forwarding paths. They can ask the fibbing controller to modify the paths according to their requirements and leverage the controller's intelligence to modify forwarding paths for traffic engineering purposes. The controller uses the information from the injected messages to compute new paths and install them as fib entries. This allows operators to customize the network behavior without having to change the underlying topology or the IGP weights. Here, we are adding another path through C to A to B and then to X. To enable traffic engineering and improve path flexibility, fibbing introduces the concept of fake nodes and links. By injecting information on these fake nodes and links to the IGP control plane, the fibbing controller can modify the topology of the network without physically changing it. For example, we can add a fake node V1 and connect it to C, then map the link V1C to the link CA. This creates a second path from C to X, which can be leveraged for load balancing purposes. To ensure that the injected information is available to all routers in the network, fibbing leverages existing interdomain routing protocols to flood the information. This allows all routers to have a consistent view of the network topology and the injected modifications. In fibbing, the injected messages by the fibbing controller create a newly augmented topology view that is seen by all IGP routers. This augmented topology view includes the fake nodes and links that have been added to the network to provide additional paths for traffic engineering purposes. The augmented topologies due to fibbing messages lead to new control plane paths being computed, which can then be translated into new forwarding paths on the data plane. New data plane paths are derived from the augmented topologies, as illustrated on the right, where D2 can be reached through two different paths. In fibbing, the controller can program arbitrary per-destination paths by manipulating the IGP's view of the network topology through injected information on fake nodes and links. The resulting forwarding paths may form a directed acyclic graph, DAG, rather than a simple path, which allows for more flexibility and optimization possibilities. However, there is a risk of creating loops in the forwarding paths, which could cause forwarding loops and network instability. To prevent this, fibbing enforces a key property called loop freedom, meaning paths to the same destination should not create loops. Remarkably, it has been proven that any set of forwarding DAGs can be enforced by fibbing while maintaining loop freedom. This opens up a rich design space for network operators to optimize traffic engineering, load balancing, and other objectives, while still ensuring stable and predictable network behavior. Fibbing offers fine-grained control over per-destination paths, allowing for highly flexible traffic steering, load balancing, and backup path provisioning. With fibbing, Any set of forwarding DAGs can be enforced to the same destination without creating loops. This level of per-destination control is achieved through the injection of fibbing messages, which augment the topology seen by all IGP routers in the network. This provides operators with fine-grained traffic steering capabilities, enabling middleboxing and per-destination load balancing. Additionally, fibbing provides backup paths provisioning for failure recovery purposes. Scalability is a crucial aspect of modern networking. In this section, we will discuss how fibbing achieves scalability in large-scale networks. A fibbing controller is introduced, consisting of three main components. The first component is the fake topology generator that applies compilation and augmentation algorithms to convert forwarding requirements into forwarding DAGs and convert the DAGs into fake nodes and links. The second component is the link state translator that interacts with the routers by injecting lies and tracking topology changes. The third component is the event manager that maintains an updated view of the network topology by parsing the routing messages collected by the translator and constructing a network graph for the topology generator. To create lies, the fibbing prototype leverages the forwarding address field of OSPF messages. The controller injects the route for the desired destination with a forwarding address and a fake cost for the fake edge. OSPF routers compute the cost of the route as the sum of their cost to the forwarding address plus the cost in the message. To support locally scoped lies, a set of IP addresses is reserved to be used as FAs, which are propagated network-wide in OSPF, but every router is configured not to install routes to all those addresses. To support the full expressiveness of fibbing, the prototype controller uses an OSPF-compliant implementation of merger with a combination of locally and globally scoped lies. Finally, proposed protocol enhancements include minor extensions that can enable more flexible fibbing in future routers, including the creation of adjacencies and a third-party next hop mechanism that allows specifying the forwarding next hop to be used if that route is selected. These changes can be added to protocol specifications without impacting current functionalities and can be deployed through router software updates. In the fibbing controller, compilation per destination is used to compile forwarding rules based on destination prefixes, heuristics augmentation is used to improve routing decisions, and cross-destination optimization is used to optimize routing across multiple destinations. The paper describes two algorithms for per-destination augmentation in the fibbing controller, simple and merger. Simple is faster and creates a dedicated fake node for every router that changes its next hop. Merger is slower but reduces augmentation size by reusing the same fake nodes for multiple routers. Simple is useful for quick failure reaction while merger can be run in the background to re-optimize the topology. The paper evaluates the trade-offs achieved by each algorithm in Section 5, which we will cover later. Consider the topology depicted in this slide showing two different paths connecting router B to router F in the left example. The control plane is optimized for the weight of the links, while in the right example, the desired path is a direct connection from B to F, even if it results in a higher link weight. To achieve this path using fibbing, the following steps are taken. In fibbing, simple is an algorithm used for per-destination augmentation that adds a fake node for every router that needs to change its next hop. The purpose of this algorithm is to quickly compute an augmented topology within milliseconds by injecting dedicated fake nodes. Specifically, the simple algorithm works by creating a virtual node for every router whose next hop needs to be changed, and then connecting that virtual node to the next hop router with a virtual link that has a lower weight than the original link. By doing this, simple creates an alternate path to the destination that goes through the virtual node instead of the original next hop router. This allows fibbing to achieve its goal of providing a more optimal path to the destination, even if it results in a higher link weight than the path optimized by the control plane. This technique can be useful in scenarios where it is necessary to prioritize certain paths over others, or where faster reaction times to network failures are required. To further augment the forwarding DAG, the fib controller can use the merger algorithm, which iteratively merges fake nodes that are created by the simple algorithm. Unlike simple, which creates a dedicated fake node for each router that changes its next hop, merger aims to reuse the same fake nodes to program multiple routers. By doing so, merger can significantly reduce the size of the augmented forwarding DAG and hence the overhead of the network. The merger algorithm starts from the output of simple and iteratively merges fake nodes based on a set of rules. At each iteration, the algorithm selects a pair of fake nodes that can be merged based on the similarity of their next hops. The algorithm then updates the forwarding rules of the routers that are connected to the selected fake nodes, and replaces the selected fake nodes with a new fake node that combines the next hops of the two original fake nodes. This process continues until no more fake nodes can be merged, or until a stopping criterion is reached. Merger is a more computationally expensive algorithm than simple, but it can achieve a more optimized forwarding DAG by reusing the same fake nodes to program multiple routers. Therefore, merger is suitable for background optimization of the forwarding DAG, while simple is useful for quick failure reaction or initial network configuration. The previous SDN solutions, such as RCP, were incapable of programming multiple next hop changes using a single fictitious node. In evaluating fibbing, the paper shows that existing routers can handle the extra load induced by fibbing. The impact on load and convergence time is negligible, and the measurements were performed using OSPF on a recent Cisco ASR9K and Juniper M120, both representative of typical edge devices found in commercial networks. Fibbing induces very little CPU and memory overhead on routers, even with a huge number of fake nodes like 100,000. The total overhead on both processes was only 154 megabytes. The CPU utilization on the router was also systematically low, at most 4%, as fibbing relies on OSPF Type 5 LSAs which do not cause the routers to recompute their shortest paths to each other. Therefore, fibbing has a very limited impact on routers, making it a feasible and practical solution for large-scale networks. The impact of fibbing on IGP convergence was evaluated in experiments conducted on real routers. The results showed that even with up to 100,000 fake nodes and destinations, there was no difference in the sub-second IGP convergence compared to scenarios with no fake nodes. This indicates that fibbing does not affect IGP convergence and can be safely used in production networks without causing disruptions. Fibbing achieves fast forwarding changes, even with a large number of fake nodes. The installation time for different numbers of fake nodes was measured, as shown in the table shown. The results demonstrate that even with 100,000 fake nodes, the forwarding changes can be installed in microseconds per entry. This makes fibbing suitable for quick failure reactions and can be used as a useful tool for network operators to manage their networks. Finally, we look at the robustness of fibbing and show how it can handle multiple failures in a scalable and efficient manner. Fibbing's ability to leverage the underlying IGP improves network robustness by minimizing the need for controller intervention in certain scenarios. This is because IGPs can quickly reconverge and synchronize the control plane, thanks to their shared topology. Additionally, fibbing supports both fail-open and fail-close semantics, which allows for more flexible network management in case of failures. Fail-open semantics allow traffic to continue flowing even if the network experiences a failure, while fail-close semantics will prevent traffic from flowing. By implementing fibbing, network management becomes simpler, and the overall resiliency of the network is improved. Importantly, fibbing can be implemented on existing networks without the need for complex SDN deployment, making it a practical solution for network operators seeking to improve network efficiency and robustness. Fibbing demonstrates the advantages of centralized control over distributed protocols, realizing an SDN management model with network-wide automated control. This simplifies controllers, improves robustness, and ensures that the heavy work is still done by routers. Furthermore, fibbing works on existing networks, avoiding the deployment hurdles associated with SDN. In general, fibbing introduces small lies to achieve better networks. And finally, as Fleetwood Mac said,